talk, which again, I have the pleasure of giving you first talk. And it will be a general introduction to the FHI-aims software package. So to give a brief introduction of myself, so I'm Konstantin Lion. I currently work as a software scientist and also industry relations officer at MS1P-EV, which stands for Molecular Simulations from First Principles EV. And you will find out also in a bit what this nonprofit association in Berlin is actually doing. But to start, we of course want to talk about FHI-aims as a code. And I want to point out right away that FHI-aims is not the result of work in one research group or by just a few individuals. It's really a collection of people with contributions of over 150 people nowadays from all over the world, from Berlin, Duke UNC, so the US, China and Beijing, Helsinki, Cardiff, Dalhousie, Warwick, and so on. So it's really a collection of people all over the world. But FHI-aims as a code has some what we call the aims coordinators. So these are Volker Blum, Sebastian Kockott, Mariana Rossi, and Matthias Scheffler, who are, some of these are also Volker Blum and Matthias Scheffler, also here as panelists today. So I want to thank them, of course, for taking the time. And I want to point out that FHI-aims as a code has really had a long history of code development. So nowadays it's more than 20 years of development. And these 150 people really has to be pointed out in more detail. So this is from our website at FHI-aims.org, where you can find the full collection of people that contributed to the code base. And this is still, we are pretty sure, not complete, but we just want to take this time to really thank those people for doing the actual work that we'll showcase here today. And to again summarize a bit what the FHI-aims code is, it's really community-based. That means it's really an open development platform. So if you're a research group, whether in industry or in academia, and you're interested in developing new research, new ideas, and you want to implement those, FHI-aims is really in that sense open for you to do your independent developments. So, and these new physics and developments are constantly being added really by scientific groups around the world without really any significant oversight by anyone. So if you're really interested in just adding science and contributing to the code, you're free to do so. Now, I already talked a bit about MS1P. So MS1P, Molecular Simulations from First Principles, is a German nonprofit association. And the main mission of MS1P is really to promote basic science. And what we do in the context of FHI-aims is we try to help with code stability and integration. So if there are issues with integrating new features into the code or just stabilizing the code in general, we'll try to help out. We are also here for community support. So we manage, for example, the community channels for FHI-aims, which is the Slack channel as well as the development GitLab channels. And we're working on documentation, webinars such as this one, online tutorials and conferences and so on, as well as, for example, here, collaboration with industry partners on specific research questions. So we're really trying to help the community as a whole that surrounds FHI-aims. And MS1P and its structure has an executive board. So that's Professor Matthias Scheffler, who's here, who's the chair of the board, as well as Volker Blum and Mariana Rossi. So that's really a brief overview of what FHI-aims and MS1P are, in case you were interested maybe what the distinction is between the two. Then let's go to the actual design principles behind what makes FHI-aims what it is. So from the onset, there was a vision that FHI-aims should be able to perform quantum mechanics-based simulations of real molecules and materials and their properties without a priori precision and accuracy limitations. And that was really something that had to be, was decided from the onset. So there were a few design choices that were needed or decided on to fulfill this vision. So one, FHI-aims should be an all-electron code. It should be able to handle non-periodic and periodic systems on equal footing. So whether you have periodic boundary conditions or not. It should scale to extremely large systems, so that can mean thousands of atoms, or as you will see later on, even 10,000s of atoms, without limitations. It should scale both on laptops as well as massively parallel HPC architectures. And in the end, the main focus in the beginning was on density functional theory, but also correlated methods. So whether you're interested maybe in RPA, GW, coupled cluster, and so on, this is also supported within the code. And the key design choice behind FHI-aims is really what kind of basis set you choose. And in this case, it's the numeric atom-centered basis functions, because they allow for an accurate representation of the orbitals as well as the densities. So let's dive right in. Let's say talk a bit more about these atom-centered orbitals. So as you might know, if you're familiar with DFT or quantum mechanics-based codes in general, you typically start from a basis set expansion, and then you have here an expansion in terms of basis functions phi I. And these phi I, you are free to choose what kind of basis functions you want to use. As mentioned, FHI-aims decided on numeric atom-centered orbitals, which are shown here on the right side. And you have a part with Ui over R, which is the radial part, as well as the spherical harmonic part. And the reason this was chosen, and you can see the structure here of the radial function down below, as that this is not an analytical function, but rather a numerically tabulated one. So you are quite flexible in what kind of choice of basis functions you want to have. And this also means that the very strong variations near the nuclei can be quite well described already with these kinds of radial functions. And we have the possibility to define, for example, here a cutoff potential to really set an exact zero at some type of radius. And what this gives you, let's say in a nutshell, is one, you have this extremely flexible shape. All these atom-centered or radial functions are tabulated on a dense logarithmic grid. So you really have the flexibility there. You naturally have an all-electron description. So within FHI-aims, there's no let's say, a distinction between what are core electrons and valence electrons directly. They're all included naturally. And of course, because these are atom-centered, so they're really localized, you can have O of n computational scaling for the most expensive steps. And that's, of course, really important for us to gain good scalability to larger system size. And in the end, because you also have, for example, here this cutoff potential, you actually need a rather compact basis set if you want to get more or less converged results with respect to here total energies in most systems. Then the important thing is you are quite flexible, but you still have to decide on what kind of basis functions you want to use for all the elements. And so for this, there are within FHI-aims, you already have a basis set library available for the elements 1 to 102. Which differ in whether you want fast qualitative results to really milli-electron converged results with respect to DFT calculations and total energy. We also have basis sets that go beyond just simple DFT. So for example, if you're interested in GW calculations and so on, we also have specialized basis sets for those kinds of calculations. So, and we hope with this, or we think that this really makes it also easier for new users to start right away, because they don't have to handle all of the specific basis set setup, but you always have the flexibility to change things yourself. So that's really one of the main key parts of the code. So you can just change stuff to your liking, of course. So and this high precision of FHI-aims for DFT calculations has already been also shown in literature. So this is, some of you might know this is the delta test, which was published in 2016. And the main part here that was checked was the energy versus volume curves for 71 elemental solids. In total, 15 codes were compared between all electron and pseudopotential codes. And here actually the FHI-aims results, which you see in the second row, were not obtained by us, but rather by Marcin Dulak at the DTU in Copenhagen. But what you can nicely see is that FHI-aims is really extremely accurate and on par with all the other all-electron code-based implementations here. So this is really, of course, one of the main pillars we want to focus on. So we want to be precise, we want to be accurate, but we also want to be efficient. So this is here the reference again for the delta test. We also have other references you can take a look at. For example, here, this is the paper on the GPU acceleration of FHI-aims. So we have partial GPU acceleration to also allow these efficient computations on newer architectures. We have, for example, also a band structure benchmark with spin-orbit coupling, if this is what you're interested in. As well as, for example, here, a relatively recent roadmap article that really describes what FHI-aims is doing to go towards the exascale. So then I wanted to point out one specific really more or less recent advancement in our eyes, which is hybrid density functional theory. So for a while, FHI-aims has been able to do GGA, LDA-based simulations for for several thousands of atoms, which with more or less optimal scaling. But the same for hybrid DFT required a lot of work. And here I want to point out this is really work over more than a decade. So this really has to be let's say, stressed that this is a lot of work by all the people involved. But we're really happy that this is in the code now. So what you see here are some benchmarks for gallium arsenide supercells with the hybrid function HC06. And what you see here is the strong scaling. So ideally, you have O of n strong scaling. And as you can see, the new implementation, and you will see also in a second actual systems, which may be more of interest than just gallium arsenide, we were able to, or the researchers, including Sebastian Kokot and others, as you will see, were able to reduce the time to solution by up to 2 orders of magnitude, as well as achieve almost ideal scaling even over thousands of cores. So as you can see, the end of the x-axis here is nearly 10,000 cores that were run on an MPCDF. So that's the Max Planck Data Facility CPU cores. So that's really, I think, amazing achievement. And the same is also in terms of scaling with the respect to the number of atoms. So not just with the number of MPIs tasked, but also with the number of atoms, we almost achieve ideal O of n scaling. And why this is now, of course, very exciting is that you can go to much larger systems than what probably a lot have thought is possible with hybrid DFT. So in this benchmark here and in this paper, these were the largest systems that were tested. So you can really see it's hybrid perovskites, it's paracetamol supercell, and then you see on the right side, both of these plots are larger ice supercells. So the largest cell that was simulated is an ice supercell with over 30,000 atoms. So that's almost 250,000 basis functions, which was able to be run on just 60 CPU nodes. So I think that's already quite amazing. And you can see that at this kind of system size, the bottleneck is really what we call here ELPA. So that's the eigenvalue solution. So ELPA here is an external library to solve the eigenvalue problem, something we'll see also later on when I will talk a bit more about the FHI-aims ecosystem. So what this now enables, which I think is very exciting, is really large-scale simulations. And for that, we need a host of features, of course, which are implemented in conjunction with these hybrid density functionals. And this is an excerpt of the roadmap, which is on advancement of the FHI-aims software package, which is, fingers crossed, soon to be published as a preprint, maybe already before Easter. So yeah, maybe you're lucky enough, and this is an Easter present for you to read. But one part is these hybrid functionals, which have support for several things, such as forces, stresses, dispersion corrections at many different levels, whether it's a D3 correction, many-body dispersion, or XDM, and all kinds of output functionality as well. And what we've already seen in recent times, so these are two recent papers, is that this now really allows other researchers to also create extremely high-quality data sets. So data sets currently, when used for machine learning foundation models and so on, are mostly based on GGA or GGA plus U level calculations. But we think now that with FHI-aims, this really allows also to do extremely high quality, hybrid density functional quality data sets. So for example, here, both these papers have used PB0 plus MBD to calculate the total energies as well as other properties. So MBD here is the many-body dispersion correction. And the first paper that we show here actually has 33.5 million FHI-aims DFT calculations in the database. And they trained this on molecules ranging with elements all over the periodic table. So the hope, and we have to see if that's actually achievable, and other researchers would try those, of course, to have a foundation model based on hybrid level DFT. So we'll see what comes out of this data set, but I think this is quite exciting development already. So this is work here from the Google DeepMind team, also in the group of Klaus-Robert Müller. And the second paper here is also from Klaus-Robert Müller, as well as Alexander Tschatchenko, where they also trained or created a data set with PB0 plus MBD for biomolecules, and then used this to train already a neural network. force field. So I think that's already quite exciting development in this direction. So that's FHI-aims and some more focus on the hybrid functionals. But FHI-aims as a whole is, of course, a large ecosystem. So you have the main FHI-aims package, which really does the electronic structure-based part. But it's FHI-aims is really based on several external libraries which are open source and which I think is critical for any kind of electronic structure code. And that includes, for one, ELSI. So ELSI is the electronic structure interface library, which gives other codes and which is also used by several codes to gain access to different eigenvalue solvers and just general things that are needed for electronic structure calculations. We also have support for several exchange correlation functionals via libxc, as well as the dispersion corrections via libmbd. And then even going beyond, in this case here, we have an interface to CC4S to do also coupled cluster calculations. And that's the basis of the driver, but FHI-aims as general also has support for external workflow drivers. So that's here, for example, IPy, the ASE Python package, Python, FHI-vibes, and so on, and many more, as well as a graphical interface, which we call GIMPs. And GIMPs is something that if you participate in the tutorial tomorrow, is something you will also then see there. And I just wanted to briefly mention FHI-aims can also be used as a library. So we have, for example, the atomic simulation interface is directly supported by FHI-aims. So if you want to extract a Hamiltonian, for example, to train on the Hamiltonian and stuff, this is also possible. We have additional Klim's Python package, which is a collection of command line tools to hopefully ease the burden of creating input files and analyzing results. Support for several workflow managers, which some of you might know quite well, like Automate2, AIDA, Task Blaster, and so on. And then lastly, something we've worked on relatively recently is PyFHI-aims. So that's really a dedicated FHI-aims I/O library, which we hope will make development much easier for the future, also for new developers. Okay, so that's the ecosystem. Now, maybe, or hopefully, I gave a good introduction to the code, and maybe you're interested in getting some more information, maybe trying out the code and so on. And there I would really suggest to go to our website. So that's FHI-aims.org, so FHI-aims.org. And here you have the option 1 to click on the Get the Code page. This will give you all the details. If you're interested, how do we get the code? Keep in mind for academic groups, it's only for a voluntary license fee. So if you're just interested in contributing and so on, you can freely do so. Just go to the website to see. And then one other thing I want to point out, which I think is very important for new users, but in general also just to showcase research, are the online tutorials which we have. A lot of them have been contributed by external people. So again, I want to point out the big work that has come here from the community. And this tutorials page is really already quite extensive and it just keeps on growing. And we're really happy that it does. And it goes from all kinds of topics, from fundamentals of FHI-aims, just how do you run the code, to how do you use different machine learning algorithms with FHI-aims, beyond DFT, molecular dynamics, complex workflow, spectroscopy, and so on and so forth. So this, I think, is a really good first step if you just also want to see maybe FHI-aims in action. And one of these tutorials, we will do tomorrow, as I already mentioned. And if you're interested, please feel free to join there. And then the last thing I want to point out is, again, our YouTube channel, because we try to also give some more visibility, maybe in a visual sense. So we created some smaller YouTube videos on the basics, on different tutorials that we had in the past, like the fusion barriers, how to calculate thermal transport, how to do these kinds of dispersion-corrected hybrid DFT calculations. So if you're interested, please also go to the YouTube channel, check them out, give us feedback, of course, if you would like to see something specific. And then with this, I'm already at the end of this short introduction. And I want to just summarize briefly. So FHI-aims is really an electronic structure code based on numeric atom-centered orbitals. And with this, I think we really enable very versatile system calculations, meaning you can do molecules, clusters, surfaces, as you will see in a second, slab systems, solids, liquids, all on the same footing. I think we've shown that we can be very precise and accurate. We can do large-scale hybrid DFT, including dispersion corrections, but also go to many-body methods. And we are scalable even on small machines like laptops, but up to 10,000, of course, on HPC systems. So with this is it for the introduction. I want to thank you all again. And yeah, the session is open for questions from your side now. Thank you. And yeah, in case you're not aware how to ask questions, so we'll use the Q&A functionality of the webinar. So if you have questions, there's a Q&A button which you can click and then just ask your questions, and we'll go through this. Yeah, and the actual Q&A will be led by one of my colleagues, which is Andrei Sobolev, and I think he can just introduce himself now. Thank you.
Yes, so if you have any questions, please feel free to ask.
Of course, if in case you don't want to ask the questions now, you can also do so later by email or by the website, where you also have our contact information, of course.
Okay, there is a question by Ahmed Mahmoudov. The question is, how well the code scales on multiple GPUs for the calculations involving hybrid functionals?
Yeah, that's a good question. So it was mostly focused on GGA functionals at the time. This is currently active work, so the GPU implementation is being worked on. It is one of the topics that we want to address also for the future. So we hope that these scaling improvements can also be there for the hybrid functions. So at the moment, I think the speed up is not drastically there for the hybrid functionals, mostly because we would have to optimize the exact exchange part to also scale well on the GPUs. So I would say this is active work. If you're really interested in using GPUs for hybrids, I don't know the exact benchmarks at the moment, but yeah, I would just say it's active work. I don't know exactly the performance there.
Thank you. There is one more question by Ashok Kumar. Can FHI-aims be integrated with crystal structure prediction methods?
Yes, thank you, Ashok. So yes, this was actually done and is being done. So one of the industry partners we have is Avant-Garde Materials Simulation, who are one of the, let's say, main providers for crystal structure prediction in industry. And they really have shown that PBE0 calculations for FHI-aims, including dispersion corrections, are really one of the ways to go to really get accurate crystal structure predictions. And I think if you maybe know also of the blind tests, the recent blind test that was done also demonstrated that, let's say, what you call the best performing team was actually the group from Markus Neumann working with FHI-aims. So I would say absolutely it can be integrated with crystal structure prediction methods. Specifically, the hybrid functional implementation is there key.
Thanks a lot. I don't see any questions open in the queue. Oh, yeah, there is one question from the anonymous attendee. Technical question. You said the radial basis functions are not analytical but tabulated. I thought they were hydrogenic functions generated by solving the H-Adam-Schrödinger equation with some modifications, additional potentials. Is this considered not analytical, or are the basis functions generated differently?
Yeah, that's a good question. So maybe, I don't know if I can refer here to Volker, who was really the main developer and who knows best about these basis functions. So maybe he can give a better answer than me there.
Yes, so you can toggle this behavior. So if you want the hydrogen-like functions with a cutoff potential that cuts off zeros and trailing zeros smoothly at a certain radius, that's best for performance, and that is done numerically. But you can toggle a switch, and then you can get analytical hydrogen-like functions also. That's documented in the manual, except then, of course, they're extended as analytical functions would be with an exponential tail, but they work.
Thank you, Volker. I hope that answers the question. If you have, of course, additional clarifying questions, feel free to ask.
Actually, I'm not sure if this was really the question. I mean, I understood the question if it is only hydrogen type of functions. In principle, actually, it's not only. I mean, you can do hydrogen functions, but what we typically do, we solve really the numerical Schrödinger equation for a free atom, right, with a cutoff potential, so that the wave functions do not range too long. But it's actually really having all the information of a free atom. And that's why they are so efficient.
Yes, yes. For the minimal basis and for the atomic-like functions, that's of course true. And there are more basis function types. I guess this question goes on. There's a question what you call analytical. For example, Gaussian functions, of course, can be tabulated on a radial grid, and we do. And Slater type orbitals can do the same thing.
Thanks a lot. There is one more question from Dr. Tagema. Is it possible to extract the radial densities and/or radial energies of systems from the output files for calculations performed using FHI-aims with DFT methods?
So I'm guessing you're interested in the actual basis function form and on what you get out and so on. I think, yes, you can extract those from within the code. I don't know what the specific keywords which you can use, but I'm sure there are some to actually output the radial functions and what we have as basis functions. But I don't know, Volker, if you have on the top of your head what's mentioned in the manual there, what kind of keywords you can use here.
So the question is, what is a radial density? I would have to ask more specifically, what is a radial density? So of course you can actually print the decomposition of the full density of an extended system into atom-centered multipoles, and then you get atom-centered multipole densities. Radial energies, I'm not 100% sure how to interpret that without a better definition, but maybe I'm just slow, which could be. But all these things can be printed if we know about them and given time, right? Often we don't know the use case, and once we know, that's actually for the other question. That's a very interesting question. I don't know if we can briefly jump over there, right? Because that asks about heterostructures, right? And as you probably saw in Konstantin's talk, we have GIMS, which includes a simple structure builder. I don't think it has a heterostructure building tool yet as a matter of being integrated there, but I think the underlying ASE has something like this. And so I don't think it should be too hard to put a heterostructure builder into GIMS necessarily. It's just something we need to know, but this is still something needed. And so it's useful to make those cases with us, and it can be done. That's actually, that second question is a very good point.
Yeah, I agree. So, I mean, the question was essentially, Leah wants to make heterostructures, but most of the programs to do so are not free. As Volker mentioned, we have GIMS, and tomorrow, if you're interested in the tutorial, we'll also go briefly through the GIMS structure builder. So what kind of structures you can build. The main thing is, as Volker already mentioned, we don't have, let's say, single button clicks to create these heterostructures. If that's really of interest, and that's something that's really good for the community, I think this can be extended. So the ASE library, as well as PipeEngine, I'm sure has utility functions to create such heterostructures. And this, of course, you can also just use. So if you are familiar with Python, so more like command line interface stuff, then you can create the heterostructures also there. This sounds more like you want to use a GUI, so really a visualization type thing. So that's possible in GIMS. You would have to do more manual work. But if you're just interested in how to create slabs, for example, so starting points for your heterostructures, this is also shown tomorrow in the tutorial. So I hope that answers the question more or less completely.